All right, so we're going to look at question number 2 here, because number 2 is going to illustrate an important concept or idea about how much force is needed to change the energy, or how much work is done and how much force is needed to change potential energy versus what force and how much of it is needed to change kinetic energy. All right, so we'll solve part A first. I think we actually did that yesterday, but we'll kind of go back to the beginning here. If I want to solve for how much work is done by lifting this 9-kilogram mass to a height of 5 meters, I just used a good old-fashioned work equals force times distance formula. I mean, F cos of theta times distance, but what's theta in this question? 0, right? Because the force and the movement are in the same direction, so the angle between them is 0. All right, so I'm just going to take my 150 meters and multiply that by 5, and that gives me 150 newtons by 5 meters, gives me 750 joules. All right, so that's how much work is done in lifting this thing. Part B asks, what's the change in gravitational potential energy? Well, it probably wouldn't ask that if this was the answer. Agreed? Okay, probably not anyway. And if it did, we'd find out right away by calculating the change in gravitational potential energy. So the change in EP is going to be m times g times h final minus m times g times h initial. But what's our initial potential energy? 0. We'd have to assume it's lifted from the ground. We're not told otherwise. Okay, so I'm just going to write m times g times h and go, all right, 9 kilograms times 9.81 times 5 meters, which I think ended up being 441.25? 45, okay, joules. All right, so here's what we have to realize then. I did 750 joules worth of work, but I only needed 441 to change the potential energy. So I didn't just lift this thing, I accelerated. I probably threw it into the air. Okay, I accelerated it upwards. Now, if I accelerated it, that means I changed its velocity, and thus it's what kind of energy? It's kinetic energy. All right, if I just wanted to change the potential energy, I could do that with a net force of what? 0, because I could lift it at a constant velocity without accelerating it. As long as I exert as much force up as gravity is pulling down with, I can change this thing's potential energy. Agreed? Right? We looked at that yesterday with the barbell doing the bench press. Right? It was 710 newtons. In order to lift it, I pushed upwards with 710 newtons. I lowered it by pushing upwards with 710 newtons. I changed its potential energy with no net force. But in this case, I obviously have a net force because the object clearly accelerates here. Okay, it's obviously accelerating upwards. Question?
Start with the net force is 0. Don't you have to be pushing slightly harder?
But yeah, just to get it going. Once it's going, then it's we're only dealing with the it's moving part. Yeah. All right. So what's the change in kinetic energy that the mass experienced? All right. Well, how can I very easily find that? Right. This is the change in mechanical energy. Remember, because work is not just force times distance, it's the change in mechanical energy. And mechanical energy is EP plus EK. Right? I would have to assume that when this thing was sitting on the ground, it also had no kinetic energy. In fact, it would have had no mechanical energy of any kind at the beginning. So all I have to do then is subtract the potential energy from the mechanical, and I'll have the kinetic. So the change in kinetic energy, okay, will be 750 minus 441.45. All right, so, oh, look at that. We still got the numbers on from yesterday. 750 minus our answer. Okay, 308.55 joules. All right, so that's my change in kinetic energy. Right? Now, for question number 3, it's asking us some stuff to do with these calculations. So is everyone okay with what I did there? Question number 2 is really just asking, do you understand mechanical energy is the sum of potential and kinetic? Now we're going to look a little bit more at the force nature of that. Okay, so it says here, calculate the net force acting on the mass. All right, the net force causes a change in what kind of energy? kinetic. That's what we have to remember here. That's what we have to get out of this question, is that a net force, okay, causes changes in EK. Because net forces cause objects to accelerate. Okay, I can change the energy of something. I can do work without a net force. Without a net force, not without a force, but without a net force, I can do work. Okay, I might just be doing work against friction, or I might be changing the potential energy of an object. But as soon as I have more force than I need, then the object's kinetic energy will change because there will be a net force, and that causes accelerations. Okay, so that's what we have to understand here. Everybody all right with that? Yeah? Okay, so if this is my change in kinetic energy, then this is caused by F net acting over a distance. Agreed? I mean, work is force times distance, and the force that causes changes in kinetic energy is net force. I have the distance. They told me that this happened over 5 meters. Can I calculate the net force acting on this object? Yes, I can. Right? I can easily do that by just manipulating, dividing this number here by the distance. All right, so I'll have F net by taking the change in kinetic energy and dividing it by the distance. All right, so we'll take that 308 and we'll divide it by 5 meters. All right, so there's our net force, 61 newtons, or 61.7 newtons. And it's up. Was there another way for me to calculate the net force here? Exactly. Okay, that's why they wanted us to draw a free body diagram, but I wanted to show you the energy relationship first. Okay, because that was the new thing. Okay, but yeah, the other way would have been that I could have had my what do we say? It was 700? No, it was 150 newtons. Okay, that was our force upwards, and then we would have the force of gravity downwards, which was 88.78. 88.29. Right, 88.29 newtons downwards, because this was a 9 kilogram mass. All right, so if I subtract those two numbers, I still get 61.7. Okay, I still get 61.7 newtons. So does my math work here? Right, this way also works, okay, as well as obviously sum of all forces, because we know that way works all the time. Okay. All right, so when we calculate, what they wanted us to do was use the free body diagram, find the net force, which was 61.7, and then calculate the work that it did. So I would take that force and multiply by 5, which is the opposite of what I did. I would just get the same number I had before. Okay, proving that, yeah, you can do it either way. Okay, I just did it backwards. So how does this answer relate to the answer in question 2C? It's the same number. Okay, I calculated the change in kinetic energy here by subtracting the potential from the total work. Okay, and then in number 3, I took the net force and multiplied it by 5. Okay, force times distance, and I get the same number. Okay, either way will work. All right, questions there? Okay. Not something you probably would have talked about in Science 10. Okay, but still equally important because we didn't ever look at sum of all forces in Science 10. That's to the right number of significant figures, right? I have 308.55, which rounds 3 significant figures, yeah? Okay, we did one like this yesterday, okay? An object on a ramp. So there's a couple of ways to do this one, but I want you guys to see, I want to see which way you use. There's more than one way, okay? Try and solve this one, right? So we got a 1,500 kilogram car pushed down a 15-meter long ramp, okay, by a force of 450 newtons. At the starting point, the car is moving at 1.2 meters per second and is 3 meters above the bottom of the ramp. Okay? Assuming there's no friction, what speed will the car be going at the bottom of the ramp? Okay, so from a diagram perspective, okay, so that's what we know. The ramp is 15 meters long. The height of the ramp is 3 meters. Okay, and the initial speed is 1.2 meters per second. We want to figure out when it's here at the very bottom of the ramp, how fast is it going? Okay, there's more than one way to do that. So first way to solve this, and I would say probably the most efficient way to solve this, is as a work-energy theorem problem. You can actually calculate all the forces and do this, like as a Newton's second law, and then just do force times distance at the end. But it takes a lot longer and there's more chances of making a mistake. Okay, so I would say right now we just want to do this as a work-energy theorem problem. Is work getting done in this question? Yes, it's being pushed down the ramp. Okay, that means that there's a force that's adding to the fact that there's more than just the energy at the top. Okay, like if this thing was just sliding down the ramp, not being pushed, the energy at the bottom and the energy at the top would be the same. It's frictionless. So it would be a conservation of energy question in that case. But in this case, there is work being done. A force is pushing the thing down the ramp. So we got to say that the work here is a change in the mechanical energy of the box. Everybody all right with that? Okay. So what's the formula for work? Force times distance. Do they tell me what force is being used to push this thing down the ramp? Do I know how long the ramp is? Okay, so I have those two pieces of information. A change in mechanical energy means taking my final mechanical energy, which is m times g times h final plus 1/2 mv final squared, right? Potential plus kinetic. Everybody with me on that? Okay, at the bottom of the ramp, and subtracting the energy at the top of the ramp. And so that would be m times g times h initial plus 1/2 mv initial squared. All right, I'm looking for this. I'm looking for how fast it's going to go at the bottom of the ramp. Everyone okay with that so far? Okay. If I want to get VF by itself, what should I move right now? Yeah, the initial mechanical energy, the initial mechanical energy is what I should move over. Since when do E's have 4 things in them? That looks better. Okay, that's what I want to move over first. How would I do that? Add it to the other side, right? Really what I'm doing in this step is going work plus the initial energy equals the final energy. That makes sense. Okay, I'm adding energy to this system. So if I add that number to the initial energy, I should have the final energy. Everyone okay with my logic? Okay. So I'm going to have force times distance plus my initial mechanical energy, which is m times g times h initial, and I have all those numbers, okay, plus 1/2 mv initial squared, and I have that number as well. All right, that equals m times g times h final plus 1/2 mv final squared. All right, this question is talking about the bottom of the ramp. What do I not have at the bottom of the ramp? Okay, I don't have any potential energy, which means I don't need this at all because it's 0. Okay, there's no potential energy at the bottom of the ramp. So all the energy at the bottom is kinetic. Okay, so I don't need that plus sign anymore either. How do I get VF by itself?
By half of it.
Divide by half of M. And then what?
Square root.
Square root it. Right? Like we said yesterday, a lot like what you would have done in a law of conservation of energy question in Science 10. Okay, just like a roller coaster question. The only thing that's different is in this question, I have to add in the amount of work that I'm doing on the way down the ramp. Okay, in a law of conservation of energy question, I wouldn't have had that. Okay, because they'd have been equal. All right, so now I can calculate VF squared. I just need to plug in all my numbers. All right, so my force was 450 newtons multiplied by 15 meters. Okay, and then I'm going to add to that the mass, which was 1,500 times 9.81 times 3 meters, because it was 3 meters higher initially, right? Plus 1/2 times 1,500 times 1.2 squared, okay, divided by 1/2 times 1,500, all square rooted. That will give me VF. All right, so we're plugging in a bunch of numbers here. 450 times 15. All right, plus 1,500 times 9.81 times 3 plus 1/2 times 1,500 times 1.2 squared. All right, divide that by 750, because that's half of 1,500, and then square root that. All right, so at the bottom of the ramp, the box will be moving at 8.3 meters per second, and that's it. Okay, I'm just looking for the speed at the bottom of the ramp. Okay, I don't have to put a direction on this. 8.3 meters per second at the bottom of the ramp. All right, other thing I could have done here, okay, is I could have looked at this from like strictly a forces perspective, and I could have found, all right, I've got this thing, and I've got an applied force that's acting down, I've got F parallel that's acting down. I could have found the net force, calculated, and gone from there, but there's just more calculating to do, because I also would have had to calculate the angle using the hypotenuse on the other side. It's just a lot more work. Okay, so you can solve this question by doing a bunch of Newton's second law calculations and then multiplying that by the length of the ramp, but it's not worth it. Okay, doing it this way involved us, doing some manipulating, but it was just one step. Okay, it was work-energy theorem and we were done. Doing this from a forces perspective means doing 5 or 6 steps to arrive at the same answer. Okay, I would never advise you to do something that takes 5 or 6 steps when you could do the same thing with 1. Okay, good question. The answer is I am. It's the F parallel that's causing my change in potential energy. And I took that into account when I did this and this, right? So I calculated the potential energy here. It became kinetic energy because of F parallel. So I took it into account. I just didn't do it from the forces perspective, right? I took that force, the pushing force, because it was the one doing the work. F parallel does the work for gravity. So when I calculated potential energy, I took into account F parallel then. Okay, so this is the energy due to F parallel. This is the energy due to me pushing the box. Yeah? All right, any other questions on how that one worked? Okay, how many people think they could probably handle one like that now that they've seen one? Oh, that's not inspiring confidence. Okay, all right, what's giving us trouble? Where did I lose everybody? Or are you all just that shy? I think it's both. Shy and lost. Sad. Afraid, cold, hungry. Yeah. A mixture of emotions. All right. Try this one. Similar type of question. Okay, we got to just roll through some examples here and see kind of how these things work. So I got a large crate rolling along a conveyor. The conveyor uses gravity by being angled 15 degrees below the horizontal to allow crates to roll down the rollers. Okay, so the crates are moving at 0.75 meters per second at the top of the conveyor and accelerate to the bottom, which is 2.5 meters below the top. Okay, there is a frictional force of 150 newtons along the length of the conveyor. At what speed do the crates leave the conveyor? All right, so these things aren't being pushed down the conveyor, they're being allowed to roll down the conveyor. So is friction going to take energy away or add it? It's going to take it away. All right, it's still a force that's going to have work done, but now I have to understand that that work is negative from a mathematical perspective. So this sets up just like the last one, but on the last one, the work was positive because I pushed it down the ramp. In this case, it's being dragged, okay? And so that's taking energy away. Okay, so we got the crate, 200 kilograms. Okay, this is 2.5 meters. VI is 0.75 meters per second. Okay, this is 15 degrees. And there's friction of 150 newtons. So think similar triangles. That angle's 15 degrees, so is this one, right? If I'm at the bottom, it's angled 15 above. If I'm at the top, it's 15 below, right? It's the same. Is that everyone okay with that? Sorry, I probably should have explained that. Okay. All right, give it a try there. All right, so am I capable right now of calculating the amount of energy initial? Okay, I can calculate the potential and I can calculate the kinetic at the beginning because I know the speed, I know the mass, I know the height, right? At the bottom of the ramp, I'm only going to have what kind of energy? Kinetic. And it's going to be less than what I have at the beginning because of the force of friction. Okay, I need to figure out how much work is done / energy is lost to friction as the object slides down the conveyor. Everyone okay with that? In order for me to know that, I need to know what about the conveyor? I need to know how long it is. If I'm going to calculate the amount of work done against friction, I need to know the force of friction, and I do, and the distance over which it acts. Can I calculate the distance over which it acts? Yes, okay. So I'm going to use trigonometry to get the hypotenuse of this triangle. All right, so the length of the ramp is the hypotenuse, okay, and I have the opposite side and the angle. So that means that the sine of 15 equals 2.5 over the hypotenuse, which is the number I need. Right, so I'm going to go 2.5 divided by the sine of 15 to get the hypotenuse. Okay, and that'll be my distance over which friction acts. All right, so 2.5 divided by the sine of 15. Okay, so the ramp is 9.659 meters long. Okay, so now that I know that, now I'm going to set up my work-energy theorem calculation. Okay, the work done, or it's in other words, the energy lost to friction, is the difference between the final mechanical energy and the initial mechanical energy. Right? Everybody okay with that? Okay. It does have less energy at the bottom, and that's because of the work done against friction. Okay, so what I'm looking for is part of this. Okay, so essentially I'm saying work equals EP final plus EK final, okay, minus EP initial plus EK initial. All right, I'm looking for something that's part of this. And I know this number is what? It's 0. Because the second point is the bottom of the ramp where I would have no potential energy. So my final kinetic, okay, is my final mechanical energy. So I'm looking for this. What do I do with this? Bring it over by adding it to the other side. All right, so I'm going to have my work plus EP initial plus EK initial. and that's going to equal my final kinetic energy. All right, so in other words, the work plus the initial energy equals the final energy. Okay. All right, the work is against friction, so this number is going to be negative. Okay, but I'm going to calculate that in a minute. All right, so I'm going to have force times distance plus m times g times h initial plus 1/2 mv initial squared equals 1/2 mv final squared. Okay, so I'm just expanding it out now to those other formulas. I need VF by itself, so I need to divide both sides by 1/2 of m, and then square root, just like I did in the last one. All right, so now I'm going to plug in my numbers. Friction is a negative force, so I'm going to make it negative when I put it in here mathematically. Okay, and it was 150 newtons. Okay, so I've got 150 times the 9.66 meters, okay, and that's negative 150, plus the mass, which was 200 kilograms times 9.81 times 2.5, because that was the height of the ramp, plus 1/2 times 200 kilograms times 0.75 meters per second. And that's squared. Okay, dividing that by 1/2 times 200. Okay, everybody with me on that? Just plugging in my numbers there. Okay, so 150, actually, sorry, negative 150, that's important, times my answer there, which was the length of the ramp. Okay, gives me that much. So that's how much energy is being lost to friction as this mass rolls down the conveyor. Okay, that's what I just calculated there. That's the work against friction. All right, now I'm going to add that to the energy I had at the top. 200, okay, times 9.81 times 2.5 plus 0.5 times 200 times 0.75 squared. Okay, divide that by 100, half, which is 1/2 of 200, and then square root. All right, so at the bottom of the ramp, the box will be moving at 5.9 meters per second. Okay, everybody all right with that? All right, now again, I could have solved this from a Newton's second law perspective and calculated F parallel, drawn force of friction up the ramp, okay, and multiplied by distances and all that kind of stuff, but it takes longer and there's more chances of making a mistake. Okay, change in energy is always the shorter way. And you get the same answer. Yeah, you get exactly the same answer, but why work for 20 minutes on something when you can work for 5 minutes on it, right? And get the same answer.
So if we use this formula, we
Nope, because you take it into account when you calculate the change in potential energy. Okay, because the change in potential energy is essentially force of gravity times this distance, which is the same as F parallel times this distance. Okay, remember that's the science behind why an inclined plane works. An inclined plane allows me to do the same amount of work, that is, change the energy of something by the same amount using less force over a greater distance, right? To push something up a ramp, I only have to push with F parallel instead of force of gravity, right? So it's less force over a greater distance. Okay?
So, sorry, how do you find the distance?
I just did trig. I knew this side of the ramp. I knew how high the ramp was, and I knew the angle, right? So I found the hypotenuse, which is the length of the ramp. Yeah. The F. Oh, the force of friction is what right. Because again, I'm taking F parallel into account when I calculate the change in potential energy, right? Okay, if you do it the Newton's second law way, then you got to go F parallel times distance, force of friction times distance, you got to do it all, right? Okay. Any other questions, Russ?
How do you know if work equals PM or work equals PM minus you know?
It's always the second one. It's work is always the change in energy. It's always going to be final minus initial. Okay. The only time I wouldn't have to put in initial is if it was 0. Right. Okay. Any other questions on that one? Those are good questions, guys. It's showing that you're thinking it through. I like that. All right. Let's take a little break. Okay. Give you about 3-4 minutes, and then we'll try another one. Okay, so we got this large round stone, okay, 400 kilograms, nearly runs him over. Okay, from a physics perspective, what height would the rock have to drop from if it rolls 30 meters? And we're going to assume that it, was just an inclined plane. We're simplifying it a little bit. Okay, rolls 30 meters against a frictional force of 800 newtons and was moving at 4.5 meters per second at the end when it seals shut the entrance to the temple. All right, so its final speed is 4.5 meters per second. We are looking for what height it had to be dropped from in order to accomplish that. Okay, so that's what we're looking for there. If you've ever gone to the Universal Studios, okay, where they have the Indiana Jones demonstration, it's awesome, okay, because they recreate that whole scene, and then they're interviewing the guy, and he's talking about how scary it was and how important it is to prepare everything. Meanwhile, there's a stagehand rolling the styrofoam rock back up the hill behind him. Like, it looks really impressive until you see the stagehand rolling this styrofoam rock all the way back up the hill, because it wasn't actually obviously a big rock. It's just a styrofoam ball that they painted gray, okay, to roll in behind them. So here's what we know. Okay, we are essentially dealing with this situation. We have a ramp. We have the stone at the top, 400 kilograms. Right? We know its initial speed is 0 meters per second, and we're looking for how high it's going to fall from or roll from, whichever. And we know that when it gets down to here at the very bottom, okay, that its speed is 4.5 meters per second, and that the force of friction acts over the entire length of the ramp, which is 30 meters. Okay, so I can't find that side using trigonometry because I don't have the angle and I don't have two sides, right? So the only way for me to find that is by using the work-energy theorem. Okay, work is being done against the force of friction down the entire length of the ramp. So the energy at the top will be greater than the energy at the bottom. Everyone okay with that idea? Okay. All right. So we've got our initial mechanical energy our final mechanical energy minus our initial mechanical energy. Now, if we're looking at this situation, that means our final mechanical energy is all in what form? It's all kinetic because it's at the bottom of the ramp. It can't fall any further down, okay? So I know that this is really just EK final. And I also know that the initial one is all potential because it's being dropped. It has no initial velocity, so all of the energy at the beginning is potential. All right, so that'll calculate the work. All right, so I'm looking for something that's part of this. Everyone okay with that? So what I'm going to do is I'm actually going to move it over here so it becomes positive and then bring the work over to this side. All right, the work is actually negative, but that's okay. All right, so we're going to add EPI to both sides, and then we're going to subtract the work. So I'm going to have the final energy minus the work should give me the potential energy. That makes sense, okay? If I take the final energy and I subtract the amount of work, that should give me what I started with, okay? Everyone all right with that? So now I'm just going to put in my formulas. This will be m times g times h initial equals 1/2 mv final squared minus the force of friction times the distance. Right, and I do have to keep in my mind here that the force of friction is negative. All right, so I'm going to have to solve for HI. So what do I have to do with the mg? Divide both sides by. All right, so there's my final formula. The initial height will be 1/2 times 400 times 4.5 squared minus negative 800 times 30, the length of the ramp. Okay. And then I divide that by 400 times 9.81, and that will give me the initial height of the rock when it was still in the trap. Okay, so 0.5 times 400 times 4.5 squared. Okay, and I'm just going to put plus 800 times 30 because it's subtracting a negative. It's the same thing. All right, and then I'm going to divide that by 400. Oh, I have to put that in brackets. 400 times 9.81. Right. So 7.1 meters is the height that the rock is dropped from, right? Which is about right. If you think about the scale, when we watched that, he heard all the noise and then he went, and he looked almost straight up to see the rock. Okay, so it was definitely dropped from fairly high above him. Harrison Ford is just under 2 meters tall. Okay, so it seems about right. Okay, questions on how that one worked? Okay, so all of these have had the same theme, okay, and that is that work is a change in mechanical energy, and then we're using that idea, okay, so force times distance equals the change, okay, in order to calculate some part of that, either a final speed or a final height or, or an initial height or something like that, okay. It's very similar to what you did in Science 10 with the law of conservation of energy questions. It's just in this case, the initial and final aren't equal. There is a difference between them, and that's the work that's being done, the energy that's either being gained or lost. Okay? But other than that, the algebra is very similar to what you would have done for a law of conservation of energy question. Okay. All right. Have you guys try a couple from the worksheet here. I'm just going to put up the worksheet and you guys can try a couple.